Here is the script cleaned and ready for voiceover. I have removed non-essential symbols like asterisk, asterisk, dash, dash, and section dividers, and kept only the natural punctuation needed for spoken delivery. Welcome! Today we're exploring one of the most fascinating and misunderstood journeys in human biology. What happens from the moment sugar touches your tongue to the cascading effects it has throughout your entire body? Whether it's the teaspoon you stir into your morning tea, the fruit you grab as a snack, or the hidden sugars in your packaged cereal, all of it triggers a complex, precisely orchestrated biological response. By the end of this video, you'll never look at sugar the same way again. Let's begin. Part 1. What is sugar? Before we follow sugar into the body, we need to understand what we mean when we say sugar. Sugar is a type of carbohydrate, a molecule made of carbon, hydrogen, and oxygen atoms. There are several types. Simple sugars, called monosaccharides, glucose, fructose, and galactose. These are the smallest, most basic units. Double sugars, called disaccharides. Sucrose, which is table sugar, equals glucose plus fructose. Lactose, milk sugar, equals glucose plus galactose. Maltose equals glucose plus glucose. Complex carbohydrates, called polysaccharides. Long chains of glucose, like starch in bread and rice, or glycogen stored in your liver and muscles. The body ultimately breaks nearly all carbohydrates down into glucose, the primary fuel of your cells. Glucose is to your body what petrol is to a car engine. Now let's follow that sugar from the first bite. Part 2. The mouth, where it all begins. The journey of sugar begins in your mouth, even before you swallow. The moment carbohydrate-containing food enters your mouth, your saliva springs into action. Saliva contains an enzyme called salivary amylase, which begins breaking down complex carbohydrates, like the starch in bread, into shorter chains called maltose and dextrins. This is why if you chew a plain piece of bread long enough, it starts to taste slightly sweet. The enzyme is literally freeing sugar molecules from the starch in real time. Simple sugars like table sugar, glucose, or fructose don't need much digestion. They are already small enough to be absorbed later. But they do something important right away. They activate your taste buds, specifically the sweet taste receptors, sending a signal to your brain's reward center, the nucleus accumbens, releasing a small burst of dopamine. That is the pleasure signal. Your brain is registering that this is energy-rich food. Good. This dopamine response is part of why sweet foods are so compelling. It is not a moral failing. It is evolutionary biology. Part 3. The stomach. A brief stop. Sugar spends relatively little time in the stomach. The stomach's main job is to process proteins and fats. Its acid environment is too harsh for carbohydrate enzymes to work well. However, the stomach does play an important role. It regulates the rate at which food passes into the small intestine through the pyloric valve. A meal high in fat and fiber slows this emptying, meaning sugar enters the small intestine more slowly, causing a gentler rise in blood glucose. This is one reason why eating whole foods with their fiber intact causes a slower sugar response than eating refined products. A meal of pure sugary liquid, like a can of soda on an empty stomach, passes through quickly. The sugar hits the small intestine in a rush. Part 4. The small intestine, the absorption powerhouse. This is where the real action happens. The small intestine is roughly 6 to 7 meters long and lined with millions of tiny finger-like projections called villi, and even tinier projections called microvilli, together forming the brush border. This dramatically increases the surface area available for absorption, the equivalent of a tennis court, all folded into your abdomen. Here, enzymes on the brush border, including sucrase, lactase, and maltase, break down any remaining disaccharides into their monosaccharide components. Sucrose becomes glucose and fructose. Lactose becomes glucose and galactose. Maltose becomes glucose and glucose. Now, in their simplest forms, these sugars can be absorbed through specialized transport proteins in the intestinal wall. Glucose and galactose use a transporter called SGLT1. They are actively pumped into intestinal cells using sodium as a co-transporter. Fructose uses a separate transporter called GLUT5, which works by facilitated diffusion. From the intestinal cells, all these sugars cross into the portal vein, a blood vessel that carries blood directly to the liver. Within 15 to 30 minutes of eating, glucose is already detectable in your bloodstream. This is the moment sugar enters the body in the truest sense. Part 5. The liver, the master regulator. The liver is the first major organ to receive sugar from the gut, and it is the body's central sugar processing factory. What the liver does with glucose. When blood glucose arrives, the liver can use it immediately for its own energy needs, convert it to glycogen through a process called glycogenesis, which is a stored form of glucose like a short-term battery, or release it into general circulation to be used by the rest of the body. The liver can store about 100 grams of glycogen. Finally, it can convert excess glucose to fat through de novo lipogenesis. If glycogen stores are full and energy is not needed, glucose is transformed into fatty acids and ultimately stored as body fat. The fructose problem. Fructose is handled almost exclusively by the liver. Unlike glucose, fructose bypasses the usual hormonal controls. It cannot directly stimulate insulin or signal satiety hormones like leptin. In large quantities, fructose is rapidly converted to fat in the liver. This is why very high fructose intake, particularly from high fructose corn syrup in processed foods, is linked to non-alcoholic fatty liver disease and elevated triglycerides. Galactose is also processed mainly in the liver, where it is converted to glucose or used in other metabolic pathways. Part 6. The pancreas and insulin. The key that opens the door. As blood glucose rises after a meal, the pancreas detects this change. Specialized cells in the pancreas, the beta cells of the islets of Langerhans, begin secreting insulin into the bloodstream. Insulin is arguably the most important hormone in sugar metabolism. Think of insulin as a key. Every cell in your body has insulin receptors, locks, on its surface. When insulin binds to these receptors, it allows glucose to enter the cell through glucose transporter proteins, mainly GLUT4. Without insulin, most cells cannot absorb glucose efficiently. Insulin also signals the liver to store glucose as glycogen and stop releasing glucose, promotes fat storage, inhibits fat breakdown, and stimulates protein synthesis in muscles. Blood glucose regulation. In a healthy person, blood glucose rises after eating, peaks at around 30 to 60 minutes, then returns to fasting levels within 2 hours as insulin does its job. When blood glucose drops too low, the pancreas releases glucagon, the opposite hormone, which signals the liver to break down glycogen and release glucose back into the blood. This back and forth is a beautifully precise feedback system. In type 2 diabetes, cells become resistant to insulin's signal over time. The locks become stiff, requiring more and more insulin to open them. Eventually, the beta cells cannot keep up. Blood glucose stays elevated, and damage begins throughout the body. Part 7. Glucose in the cells, making energy. Once glucose enters a cell, it undergoes cellular respiration, the process of converting sugar into usable energy in the form of ATP, adenosine triphosphate. This happens in 3 main stages. First, glycolysis in the cell's cytoplasm. Glucose, which has 6 carbons, is split into 2 molecules of pyruvate, each with 3 carbons, producing the small amount of ATP. Second, the Krebs cycle or citric acid cycle in the mitochondria. Pyruvate is further broken down, releasing carbon dioxide and generating electron carriers. Third, the electron transport chain on the inner mitochondrial membrane. The electron carriers donate electrons through a series of proteins, driving the production of large amounts of ATP, about 30 to 32 ATP molecules per glucose molecule, and producing water as a byproduct. The end result: one molecule of glucose becomes carbon dioxide, which you breathe out, water, lost in breath, sweat, and urine, and 30 to 32 units of ATP energy, the chemical currency your muscles, brain, heart, and every other organ use to function. Your brain alone consumes about 120 grams of glucose per day, roughly 20% of your body's total glucose usage, despite being only 2% of your body weight. Part 8. What happens when there's too much sugar? Long-term effects. Occasional sugar intake is handled beautifully by the body. But chronically elevated sugar intake, particularly from refined sources, has serious consequences. Short-term excess. Prolonged high blood glucose causes glycation. Glucose molecules attach to proteins and fats in a non-enzymatic process, forming advanced glycation end products, or AGEs. These damage blood vessel walls, nerves, and organs. Insulin spikes are followed by reactive drops in blood sugar, the sugar crash, causing fatigue, difficulty concentrating, and hunger. Long-term excess. Insulin resistance, where cells downregulate insulin receptors in response to constant high insulin levels, reducing sensitivity over time. Type 2 diabetes, where chronic insulin resistance leads to persistently high blood glucose, damaging blood vessels and nerves throughout the body. Non-alcoholic fatty liver disease, as excess fructose and glucose are converted to liver fat. Cardiovascular disease, as elevated triglycerides, inflammation, and endothelial damage from glycation increase heart disease risk. Dental cavities, as oral bacteria ferment sugars, producing acids that dissolve tooth enamel. Weight gain, as excess glucose stored as glycogen eventually overflows into fat storage, and high insulin levels also inhibit fat burning. And neurological effects, as some research links chronically elevated blood glucose to increased risk of cognitive decline and Alzheimer's disease, sometimes called type 3 diabetes in research literature. Conclusion. Let's recap the incredible journey. Mouth. Enzymes begin breaking down starch. Sweet receptors trigger dopamine. Stomach. Regulates the speed of passage. Fiber and fat slow it down. Small intestine. Enzymes complete digestion. Glucose, fructose, and galactose are absorbed into the portal vein. Liver. Processes fructose almost entirely. Stores or releases glucose based on need. Converts excess to fat. Pancreas. Releases insulin in response to rising blood glucose. Cells. Insulin unlocks glucose entry. Cellular respiration converts glucose into ATP energy. Long-term, chronic excess disrupts this system, leading to insulin resistance, metabolic disease, and organ damage. Sugar, in appropriate amounts from whole food sources, is a perfectly normal and necessary part of human metabolism. The body is remarkably well designed to handle it. The challenge in the modern world is the sheer volume of added, refined sugars now embedded in our food supply. Quantities that no evolutionary pressure prepared us for. Understanding the biology does not mean fearing food. It means making more informed choices. Thank you for watching.